Okay, this is the 2015 Physics 2 free response question number 2. So we have our little circuit set up here. All these 3 light bulbs are the same resistance. We start out with an open switch here, and then we're going to close it. So student makes the following prediction: bulb 1 will decrease when the switch is closed. Do you disagree? Well, when we close the switch, essentially we're going to create a parallel circuit here. Because of that, the overall resistance, this resistance is going to decrease, which means the overall resistance will also decrease, which means, well, the brightness of this bulb should increase. Okay, so I disagree because of what I just said. Okay, because the overall resistance will decrease when bulb 3 is in parallel with bulb 2. Therefore, the total current increases and the power of bulb 1 will increase. Okay, there's also another reason as well, and that would be the voltage drop across these. When this resistance decreases when it's in parallel, the voltage drop across it will also decrease. Because of that, the voltage drop across this will therefore increase, and therefore this one will become brighter. Okay, and actually probably for 2 I'm going to derive that. I'm going to use voltage here, so let's start with P equals V squared over R, right? So before the switch is closed is P1. Derive an expression for the power P new expended by bulb 1 after the switch is closed in terms of B1. So this is going to be P1 is equal to V of 1 over R of 1. Actually, I'm just trying to think, should I maybe do the I squared R? Is that going to be a better way to go with our derivation? We'll just do it with V1. So so this should be initially P1, right, is going to be V1 is going to be V total, right? Or let's just use EMF over 2 squared, since initially they're going to split and have even voltages, right? This would be epsilon over 2, this would be epsilon over 2. So that's going to be our initial power, P1. Okay, and then P1 after, call this initial, P1 final. So that's going to be this situation. That's R1, right? R2, R3, actually these are all the same. So this will be R. This is a parallel circuit, so this would be R, and this would be R over 2. Right, and so proportionally speaking, since this is half of this R, this is going to have to take twice as much of this. Right, so this should be 2/3 epsilon. This should be 1/3 epsilon. And so that's going to take that amount of voltage, that's going to take that amount of voltage. If this is our starting, right, this should take twice as much as this. Okay, so P1 final is therefore going to be 2/3 epsilon squared divided by R1, or R, I guess. Okay, so anyway, what are they asking for? Derive an expression for power expended by bulb 1 after the switch in terms of P1. So we just want to put that in terms of what we have over there. Okay, so this is going to be what? 1/4 E squared over R. This is going to be 4/9 E squared over R. So since E squared over R equals 4 times P1, I know this is probably not how you should be doing this. We should be organizing this a little bit better, but we'll go ahead and place that over there, right? So there we go. So P1 final should equal 4 times 4 P1 over 9. 16/9 P1. Student makes the following prediction about bulb 2. Bulb 2 will decrease in brightness after the switch is closed. So that's true. Sorry, here we go. Student makes the following prediction. Bulb 2 will decrease after the switch is closed. Do you agree or disagree? So I agree. So what's going to happen here is when this gets closed off, this is going to essentially share the current with number 2, right? Some of the current's going to go through here, some of the current's going to go through here, and it's going to have to go down. The overall current through here, it's going to have to share it over with the other one. Okay, because bulb 2 will now split the current with bulb 3, where before it got the full current. Now, even though the full current is going to be more than it was before, it still has to share that, and the net result will be less. And we'll kind of justify that with a calculation here. Okay, and that's what they want us to do next. Let's go ahead and justify this with the calculation. So yeah, so we're just going to look for the power on bulb 2. So before, I mean, using our previous values, P1 before would have been exactly the same, right, for bulb 2. So that was, what was that, 1/4? 1/4 epsilon 2 over R. So that's our P2. before. We'll put that initial. So in our other circuit, let's just kind of use that other circuit that we had before. So this voltage right here is now going to be, since these are in parallel, this is going to take on that same voltage drop. So this will be the voltage drop, the 1/3 epsilon that we have right there. So let's just do what we did before. So this is going to be P2 final. This is going to be 1/3 E squared over R. Oops, 1/3 E squared over R. Okay, and like we said before, the E squared over R is equal to 4P2 naught. So that's going to be 1/9 times E squared over R. And we'll make that substitution, and we're left with 1/9, 4/9 P2 initial. Okay, alright, that brings us to our final question. We're now going to put a capacitor here. How does the brightness immediately after the switch? So again, here's our circuit. This is 1, this is 2. We're now going to stick a capacitor here. So how does the bulb compare to the brightness immediately after? So remember, when it's immediately after, that's the key word, immediately after, the capacitor acts like a short. So as soon as you close that switch here, the capacitor acts like a short. So this is just going to go straight through there, right? It's going to bypass 2, so 2 won't even light up immediately after. So it's going to dim way down. Okay, actually it's going to turn off momentarily when it's shorted out, right? So bulb 2 will be dimmer than 1. Actually, it should completely turn off, right, immediately. Okay, so 1 will be much, much brighter, right? Short circuit. I think I've justified it by saying that acts like a short circuit. Okay, after a long time, well, it's going to be equal. Okay, the capacitor now acts like a open circuit. So when it acts like an open circuit, the brightnesses will be equal. Okay, so what's going to actually happen, this is going to turn off immediately, and then as the capacitor slowly charges, this is going to start to get brighter and brighter and brighter, and this is going to get dimmer and dimmer and dimmer, and they will eventually reach the same brightness. Okay.